All right, let's go ahead and get started. I do want to welcome you to this worksheet. This is acid-base theories. There was a previous worksheet that was called acid-base theories, so we're going to call this one acid-bases theories part 2. All right, so let's go ahead and start. First of all, what do we mean by Arrhenius acid? Well, we've discussed in the last worksheet that an Arrhenius acid contained hydrogen and will cause an increase in the hydronium or the H3O plus or H plus concentration. So remember that when H plus comes into contact with water, it's going to form almost exclusively H3O plus anyway. So we're going to say H plus or H3O plus concentration in the aqueous solution. So that's the Arrhenius acid. How about a base? Well, an Arrhenius base is one that will cause an increase in the hydroxide ion concentration or the OH minus concentration in aqueous solution. So again, from the Arrhenius standpoint, if we see an increase in the H3O plus concentration or H plus concentration, we call it an acid. That's an Arrhenius acid. If we see an increase in the hydroxide ion concentration, we're going to call that an Arrhenius base. All right, that's going to be an Arrhenius base. So there we go. Let's take a look at this now from the Bronsted-Lowry point of view. The Bronsted-Lowry acid, this concept of acids and bases is that all acids are proton donors, all right? So acids are proton donors and bases are proton acceptors, right? Slightly different way of looking at acids and bases, although there is considerable overlap between the two. We're going to look at that in just a moment. Let's talk a little bit about what happens when you add an acid to a base. We're going to call that a neutralization reaction. Well, neutralization reactions are reactions in which you combine an acid with a base to form a salt and water. Now, this is interesting because remember that the salt is neutral and the water is neutral. We took an acid and a base and we formed salt water. That's neutral in pH. It has a pH of 7. So we call that a neutralization reaction. It's going to happen every time we put an acid and a base together. So let's look again at the definitions of Arrhenius acids and Arrhenius bases. We said that an Arrhenius acid was an acid that produced H plus or H3O plus in aqueous solution. And an Arrhenius base produces OH minus in aqueous solution, right? It's a hydroxide ion producer. So that's the definition of an Arrhenius acid and base respectively. How about Bronsted-Lowry? Well, the Bronsted-Lowry definition of an acid is that it's a proton donor, right? It's going to donate a proton, or at least one proton, to a base. So in order for there to be a donor, there has to be an acceptor. The base is that acceptor. So a base then would be a proton acceptor. All right, so those are the definitions. Let's look at number 2. Number 2 says, in the following chemical reaction or equation, we have hydrochloric acid and H2O yields H3O plus Cl minus. The Arrhenius acid then would be the hydrochloric acid. Remember, the definition of a hydrochloric acid is that if we produce H3O plus when we add it to water, well, it's an acid. That's the definition of an Arrhenius acid. And likewise, if we have a chemical reaction like number 3 where we have ammonia plus water, this is an equilibrium with NH4 plus and OH minus. Remember, first of all, we're getting an OH minus. That's the definition of Arrhenius base. When you produce OH minus, that's a base. Notice the arrow going both directions. That means equilibrium. That means that it's going back and forth in an equilibrium, right? Why? Well, there's a difference between number 2 and number 3. Number 2 is starting with hydrochloric acid. That's a strong acid. That means complete dissociation. Complete dissociation is what we mean by strong acid. But in 3, we've got NH3, which is a base, but it's not a strong base. It's a weak base. Thus, the equilibrium, right? Thus, the equilibrium. Nonetheless, we are forming OH minus on the right-hand side. That's what we call an Arrhenius base. So NH3 is the Arrhenius base. That'll do it for number 3. So we've got 2 and 3 behind us now. Let's go to number 4. Number 4 says, in the following chemical equation, we've got hydrofluoric acid plus ammonia yields NH4 plus F minus. The Bronsted-Lowry acid would be what? Well, remember that the Bronsted-Lowry acid is the proton donor. Is hydrofluoric acid donating a proton? You bet, because when I look at it on the right-hand side, I see F minus. Who's it donating it to? It's donating it to the ammonia, right? So the ammonia is accepting the proton. I know that because when I look on the right-hand side, I see NH4 plus, right? NH4 plus. So What's the Bronsted-Lowry acid? It's the hydrofluoric acid. So let me put that right there. That's the hydrofluoric acid. And the Bronsted-Lowry base then would be the ammonia, the NH3, just like that. Let's look at number 5. Are all Arrhenius acids Bronsted-Lowry acids? Why or why not? Well, we've alluded to this already. We know that there's overlap, but what does that overlap look like? So the answer to the question is yes. All Arrhenius acids are also Bronsted-Lowry acids, and all Arrhenius bases are also Bronsted-Lowry bases. Because all Arrhenius acids will increase hydrogen ion concentration in solution and therefore must be proton donors in order to accomplish that. All right? So that's it. All Arrhenius acids are also Bronsted-Lowry acids. All Arrhenius bases also Bronsted-Lowry bases. The reverse, however, is not true. Okay? So Bronsted-Lowry definition is wider, includes more things that the Arrhenius definition doesn't. So let's name Arrhenius and Bronsted-Lowry acids and bases. Let's start with sodium hydroxide in A. NaOH is an Arrhenius base. I know that because Arrhenius base says that I'm going to produce OH minus. That's the OH minus that's going to be produced. So A would be an Arrhenius base. So we're done with the first one. Let's look at B. B says we have NH2. Now remember that NH2 is going to accept a proton, right? It's going to accept a proton. Well, what do you call that? We call that a Bronsted-Lowry base. Remember, a base is going to take on a proton. It's going to go from NH2 to NH3. So we're going to call that a Bronsted-Lowry base, right? Let's take a look at the next one, C. This is H3PO4, phosphoric acid. It is an acid, but it's both a Bronsted-Lowry and an Arrhenius acid. It's going to donate a proton, right? It has 3 to donate. It's going to donate a proton to a base, so that makes it an Arrhenius acid. But it also is going to increase, it's an Arrhenius acid because it's going to increase the hydrogen ion concentration. It's a Bronsted-Lowry acid because of the fact that it's going to donate a proton. Nonetheless, we're going to call it an acid because it's both Arrhenius and Bronsted-Lowry. Let's look at D. Same thing. We've got HBr. We know it can donate a proton, so that makes it a Bronsted-Lowry acid, but it's also going to increase hydrogen ion concentration. So we're going to call that an Arrhenius acid. D is done. Let's look at letter E. We have CaOH2. Obviously, the OH2 is going to render this as an Arrhenius acid, right? It's going to be an Arrhenius, an Arrhenius base because it has OH minus to contribute. It's going to increase the hydroxide ion concentration. That makes it an Arrhenius base, so we're going to call that AB or Arrhenius base for letter E. Now F. Now this was an interesting one. It's just plain water, right? But water can act as an acid or a base. It's what we call amphoteric, right? Amphoteric, which means it can act as both an acid and a base. In fact, it can act as an acid from the Arrhenius standpoint or the Bronsted-Lowry standpoint. So we're going to call that, we're just going to say acid for the acid side. And for the basic side, we're going to say it can be also a base, a Bronsted-Lowry base, or it can be an Arrhenius base. So it can be anything, right? So water is considered anything, right? Let's take a look at number 7. This is predict the products of the following neutralization reactions. Don't forget to balance the equation. So here we go. Number 7 says this. We've got hydrochloric acid plus sodium hydroxide, an acid combining with a base. Now here's what we need to know from this problem right here. When an acid and a base come together, when they react, something interesting happens. We form a salt. That's what the sodium chloride is. It's a salt. And we form water, right? Now what's interesting is we took something that was acidic and something that was basic. We combined them and we formed sodium chloride, a salt, and water, right? That's salt water. That's neutral. So we formed a neutral solution from an acid and a base. We call that neutralization. We call that neutralization. Does that make sense? So that's number 7. Number 8, we have hydrogen bromide and barium hydroxide. We have an acid and a base, right? So this is the acid and this is the base. So what's going to happen? Well, when we have an acid and a base, we put them together, we're going to form a salt. That's what this is, the barium bromide is the salt. And of course, we're going to form water, right? Just like that. So when we form salt water, we've gone from an acid and a base to a neutral salt water solution. So what is the balance reaction? It's 2 to 1 to 1 to 2, right? So again, we call this a neutralization reaction because we're going from an acid and a base to salt and water, neutral. All right, last one. Let's take a look at number 9. We have HClO4 plus NaOH. We're going to form salt and water. We're beginning to see the pattern here. So salt here, so this is the salt, and we're forming the salt from the cation from here and the polyatomic anion from here. That's the salt, and water is formed from the hydrogen here and the OH here. So this is the water. Once again, the lesson here is that when we get a salt, when we get an acid and a base, and we put them together, we get a neutral solution of salt water. That's what happens when you put an acid and a base together. That'll do it for number 9, and that'll do it for this worksheet. I'll see you on the next one. Thanks. Bye-bye.